So, good afternoon, everyone. Thanks for joining my talk. So, I would like to start from one most important thing is actually really thanking you for coming and staying. And I hope I will entertain you and you'll learn a thing or two. So, my name is Matthew Tovbin. I'm an engineer in Salesforce Einstein platform team. And we build machine learning capabilities for Salesforce. And today I'm going to be talking about how we implement automatic machine learning techniques at Salesforce. I would like to start from this forward-looking statement, which basically means I will summarize it for you. It says that whatever I'm going to say is, might have some futuristic view of things. And whenever you think about implementing your machine learning applications, always remember that don't base your product based on what I say. I would like to start from this great quote, so we can appreciate it for a moment. I will read it out loud. This lonely scene, the galaxy is like dust, is what most of space looks like. The emptiness is normal. The richness of our own neighborhood is the exception. So I like to take a real moment and appreciate this because I'm so delighted to be working as a machine learning engineer, and you as data engineers and data scientists should also appreciate it for a moment how much richness do we have in our own world. And we have such interesting problems that we solve, such as autonomous cars and predictive capabilities and so forth and so on that we build in for our platforms and in our day-to-day life. So this quote is actually from a documentary called Powers of 10 of 1977 by Ray Eames. And I really like this documentary because it actually, what it does is that it shows you the richness of our world. It slowly starts from our normal scale at a human hand, and then it slowly zooms out to the size of the observable universe, and then drops back into the level of quark, which kind of gives you a good scale to see how complex our world is. I would like to draw a similar analogy to machine learning. So when we think about machine learning, we sometimes think in partial, solving the equation partially, or thinking from the scope of our experience. But overall problem is actually quite complex if you would like to solve it in a generic way. For instance, just to start doing machine learning application, you need to start and define your data collection, data preparation. Then you would go and start doing some feature engineering for your machine learning algorithm. You would need to take care of how to select your features, how to evaluate them correctly. You would be worried about sampling, correct algorithm implementation, how to tune parameters for those algorithms so your applications will run faster. Eventually, you would need to build up certain metric, how to select proper models, and you will get into the model serving problem, right? How do we serve our scores fast? How do we serve our models? And then we get to the prediction insights and metrics, right? So how can we get some visibility into our model performance? So these are like big problems, one of its own, similar to what Powers of 10 gives us when we look on every single level of scale in our universe. It can be a bit summarized, so our day-to-day work might be a bit different, and then each time we go and approach to build an actual application, the predictive capabilities for our systems, we would go through a set of steps. We would start by defining some requirements and outcomes that we want. You better define outcomes, by the way. So a lot of people do this mistake, like expected outcomes. And then we start collecting and exploring our data. And then there's this cycle that we go through where we define some hypothesis on an application, something that we want to prove or disprove. Do we have a negative or positive ROI on this problem? Do we have our users coming back to the website based on certain behavior or not? Do we want to emphasize on this behavior or we should not? And so forth and so on. So we define this hypothesis, and then we prepare the data for the predictive application and want to build on top. Then we end up building prototypes. So this might take some time, right? We build a prototype, then we run it, we verify our hypothesis. If it's, usually we disprove it, well, and then we go back to define a new hypothesis, and we go through the cycle until we find a good predictive model with a good use case that is proven to work, and then we train and deploy the model. So at Salesforce, we do the same thing, but we do it all over again, thousands of times for thousands of customers. So it's very difficult for us to do it manually. So like, look on those brands. I just put some brands that we have supported by multiple of our clouds. So Salesforce consists of multiple clouds. And on each cloud, say marketing cloud, a sales cloud, or service cloud, each of the clouds have different predictive needs for their customers. And one customer can be can be a tenant in multiple clouds and so forth. So we have those very vast and diverse data sets across all of the Salesforce clouds. And then the use cases and the predictive capabilities differ a lot. So for example, apps for US Bank would be very different for the nonprofits such as American Red Cross or L'Oreal. So question to an audience, make an intelligent guess right now. You can shout it also, like, how long does it take to build a machine learning application? Weeks, okay, good guess. I hear weeks here. It's a months or more, right? Hours, well, that would be awesome. That's actually what we all want, I guess. Just wake up in the morning, drink a cup of coffee, drive to work, code a little bit, and voila, we have an app. The thing is that you see this image here, it should hint you on the right answer. It's an image of the black hole. I didn't take it. It's a NASA. So it's actually months on average. So for us, we kind of looked on it, and across the teams, we've seen it takes months. It takes 3 to 10, sometimes more. And it's different problems, product, definitions, data access. So some companies it might take more. So here's another example, right? So we said, okay, how do we break this vicious cycle of having something that, I don't know, it's not playing the GIF here. It actually should be an animation. Well, I guess you have to believe me that it's an animation here. So our product came up with this idea, okay, well, how do we make this really fast? How do we give machine learning access to our customers so they can prototype their ideas? So we won't even get involved. So they came up with this idea, okay, maybe we build a product called Einstein Builder, and the customers will do point-click predict. They will select some fields, and then select a prediction field and click submit, and everything else happens automatically. Sounds like a great idea. As an engineer, when I hear this, I get a shock. So, and my first shock is that how are we going to build this? Because we're talking about thousands of customers, thousands of data sets, different sizes, different varieties, and making this completely hands-off sounds like a very difficult idea, considering also this whole cycle and difficulty of building machine learning applications. So we're actually doing this. We're crazy enough to believe that it's possible. So the main question we ask ourselves as engineers is that how do we cope with this complexity? Is there a secret sauce or method that we can just grasp and use and like an equation, right? So something that lets us deliver machine learning applications in hours. And I want to put another quote here. So the task of software engineering development team is to engineer the illusion of simplicity by Grady Butch. He's the author of UML. I like this quote a lot as well, because this is defines the work I do. I just literally, every day I come to work, I hide the complexity by adding some abstraction layer, maintaining another abstraction layer, and so forth. But it's actually very powerful. It's actually a very powerful idea to hide complexity so we can actually open our minds and free our minds to greater things, right? To be more creative. To become more creative, we need to get this space in our minds. So this is actually like this balance between complexity and abstraction. So from left to right, we have, I just like put some paintings here to set a scene of, okay, we have various levels of complexity that goes more and more abstract. We can still see the idea of some concepts as we go. So like a Picasso painting, this happy man flying through the stars with an open heart. He's probably in love, and you can make up a story which would be coherent to this image. But then when you look on the black square of Malevich, it's not obvious, like, what do you want to think there? It's like a black box. So obviously, we don't want that kind of abstraction. We want something very flexible, or relatively flexible. We don't want very flexible because, right, it won't probably suit our needs. But then we want to find this balance. We want a balance between the abstraction. We want to deliver some syntax, and language, using the language and semantics, for example, which define the degrees of freedom within our applications. And the higher degrees of freedom we get, the lower abstraction is imagine like language like C or C++. You can build very complex applications with it, but it's just very difficult sometimes. You need to get a lot of experience once you get proficient with a framework. And then the higher level of abstraction, you can think of some language like SQL. So SQL is extremely powerful, proven over years, and we've seen greater adoption in the vast majority of data and machine learning applications where it's much less flexible. You cannot build controllers with it, but for what it can do, it's amazing. And then like XML might be like a bad example, for example, right? It's like something like a hairy thing where I would not put it on the slide even. So we made up this library. So we developed this library called Codename Optimus Prime. It's a automated machine learning application on top of Spark. So the main idea is basically to cover all those use cases that I mentioned before, and to provide this good level of abstraction with a declarative and intuitive syntax for machine learning specialists and engineers to work on. So they won't have to write their prototypes in Python and then recode it into Scala and so forth. We wanted something like one language for all the teams to work on, and also make it easy to express your ideas. And I'm going to demonstrate further what I'm talking about here. So one of the first things that we did, we had to define type hierarchy. And like going back to this Grady Bridge slide here, this is a lot of complexity here right away. I actually removed some of the errors here. But we had to think to the minds of machine learning engineers and think, okay, what kind of abstractions do people want to have and they want to expect when they build machine learning applications? So we came up with those types. And those types actually give us a lot of power when we build our features for machine learning apps. So we took those types and we put them everywhere in our library. So I would like to highlight three main things. There's like value operations, feature operations, and transformations. So in every single level, we wanted to have type-safe guarantees on our operations. So I put like simple examples here on the tokenize, for example, when I would write a tokenize function that would get a text and get a text list. So all those operations are checked by compiler, and it's very expressive. And then going forward and then looking on the feature, for example. So feature you can think about as like a pointer to a column in your data frame. So all operations and features should also ideally be type safe. So in this case, I would define a feature named title, and I want to tokenize all the values in this column using my tokenize function. And it's actually very easy for me to do. It's very much comes natural, especially for those people who code some functional language. And then same for transformation pipelines. We want to get compile time errors when we stitch incorrect features together. Something that doesn't match, we want to get notified right away at compile time, not 10 hours after you run the model in production, right? Because that's going to too late. Runtime exceptions are horrible, your executors fail. I'm talking about in the context of Spark, of course. I kind of presume some that kind of implies from the conference name. But it's not necessarily Spark related, right? Something like long running jobs, like you run TensorFlow, same thing. So, and then let's just look on one simple example. So I built this little example of book price prediction. And this is literally the whole code that I had to write this regression application. So what I want to predict here is I want to take author, title, and description of the book, and I would like to predict the price. I just want to see how, kind of obvious things, right? Maybe some authors are more expensive and so forth. So I would start by defining the features, and then I would do some feature engineering, which is very natural, similar to the same operations you would do for value types. So I would concatenate title and description, for example, and tokenize it, and then run some TF-IDF. And then the rest, I run some magical transmogrify and run SentiCheck. And then finally, I spin up Spark and train my model by doing this like regression model selector, which will go through multiple models and train them. So there is some magic here. So like transmogrify, you might notice like what is this beast, and then SentiChecker and so forth. So these are actually like components that we found to be very, very important. And they're not necessarily tell you anything, and that was the idea. It was like actually idea to signalize, okay, here's some magic going on, maybe read the docs and so forth. Because they're not similar to anything that we know so far. What transmogrify does, right, it actually takes care of automated feature engineering underneath. So I'm just like, I put this little diagram to explain what was happening on the code slide. So when we read our data, say like the books, the raw data, we materialize the features, and then the transmogrify shortcuts make sure that all the stages are applied in the correct order, and then the final feature vector is combined correctly. And then SentiChecker is another kind of magical, you can call it magical, right? Stage that computes a bunch of correlations of your features and actually does the feature selection for us. And then the rest of the pipeline hits in. It's all wrapped into this workflow abstraction, which eventually produces us just the model, right? So it's like a very simple way of thinking about machine learning applications. So in essence, Optimus Prime covers three main areas. So we cover automated feature engineering, feature selection, and then model selection. I'm going to briefly speak about all three of this. So when we do automatic feature engineering, thankfully, since we know the types, we can do a lot of type-specific operations. For example, if the type is email, we might define, okay, we might apply an estimator, like some method that verify that email is spammy or not, or extract the top domains. And the phone number, we can also do some kind of verification. And for example, for numerical fields such as age, we will do automatic bucketization of values, which usually improves models, and so on and so forth. And we build it that way so it can be very easily extensible by the developers who developed this thing. And then we kind of went forward, and then we developed a bunch of other operations that we find to be very useful across the teams that we worked with, like such as temporal and spatial features and categorical and so forth. This is all possible only because we keep a lot of metadata. So whenever we run our feature engineering and feature selection, we actually compute a bunch of metadata, which is like we also ship it as a part of our models. And it's something that some of you already do anyways, right? When you write your bucketizer or something like this, or auto-bucketizer, or you write your TF-IDF transformer. So when you compute your terms, this is somewhat metadata. So for us, it was like a very important piece to have. And then next thing is automatic feature selection, where we go and we compute a bunch of features across those feature values, depending on what feature type is this. So usually it's a correlation or Kramer's V for categoricals and so forth. One specific thing that we actually have at Salesforce is the data leakage. So this is something that we had to take care of. I don't know how important it is for your organization, but for us it was a very important problem to solve, where the data gets I don't know how to, well, I can put it simply like this. So let's say you want to predict certain field, but some other fields gets updated before this final field is updated. I hope I'm making sense right now. I don't want to confuse you with more specific example. So we actually build a bunch of statistics to eliminate the label leakage. And then for the users, this looks like very simple. They just write one single function application with a bunch of arguments that they would specify, and they get their data logged and so forth. The next step is the model selection. So in regular Spark, you would usually train a model or two, and you have to manually specify each model and each algorithm, and for each algorithm, you would specify a grid. So we're actually automatically taking care of that, and we're trying to find the best suitable model and algorithm with the best suitable grid for the problem. And we keep expanding this. And again, from the user perspective, it's very simple to specify. Where it's like from one builder, from one factory, you would go and specify, okay, I want a regression model selector and what kind of data preparation you would like, cross-validation or train validation split, and you can specify a custom splitter, and so on and so forth. And we've seen it to be very important when we run our models. A lot of times, specialists and data scientists go from the algorithms they know, so they would apply machine learning algorithms such as logistic regression, linear regression, but then they would not even evaluate things like decision trees, and then our model selectors automatically verify those algorithms for you. So there is no extra code has to be written for this. I'm going to show some demo now about the Titanic data set. And let's see if I have it. So this is a little application I did. So I hope you're all familiar with the Titanic problem, right? So Titanic is based. We want to predict the survival of passengers on Titanic, and we know all the passengers and all their some information about them, such as age and number of siblings and spouses and their gender, and the port that they embarked and the cabin. And what we'd like to predict is we would like to predict the likelihood of survival. So what I started from is that, again, I started from building a feature. So I started by defining my features. Okay, I want to have a survived feature, which is a response feature. And then I define the passenger class and the passenger name and so forth. After I'm done with that, I went and I defined actually the application. So this is literally the whole code I had to write here. I defined a simple reader to read my passenger type from a CSV. Then I just for fun created some features. Then I ran the sanity checker to verify to do the proper feature selection. Apply the data splitter, ran the model selector, and then stitched it all into the workflow. Actually, I added an extra evaluator here. And this is literally the whole code you have to write for this. So let's see. I'm not going to run it. You have to believe me that it works, because it's going to take a minute. So this is the output of this app. And then I'm just going to briefly run through the output, what we get here. So we get the output that it shows the best model with all the metrics that it computed, such as AROC and UPR. And then on the top, we can see all the other competitor models that it tried. So a bunch of random forest models with different different parameters. Scrolling up, I would see a bunch of statistics, confidence statistics and feature statistics that Sandy Checker computed. And I'll try to find remove. Yeah, so for example, some features were removed. So Sandy Checker decided that the variance of those features are below a certain threshold, and it was just removed. And overall, we find that this approach to be very, very helpful, especially considering the amount of data that we crunch through. What else I want to show you? I actually made it pretty verbose. I probably should have logged a shorter version of this. Okay, let's get back to this. Oh yeah, and maybe I'll show you a thing or two how easy it is to modify stuff. Let's say I want to do. Let's say I'm not happy with my model, so I want to do some like name pick list, and I want to do some modification on the name feature, so I can use this map shortcut to do map this feature to a pick list type, and then get this to pick list. I don't know, just doing some stupid things, but and then I do a pivot on this. Maybe I would say top k of 10, and I can go and see what are the arguments I might have for the pivot function, and then I would just like put it into the vectorize, and nothing else I need to change. So I can just recompile and rerun it. Okay, well, I'm not going to run it. Well, let's see. So how well does it work? It actually works pretty well. And then most of our models that we shipped are completely hands-free. And we've been kind of announcing about this and shouting around about this. So we're pretty proud about the performance of this library. And we currently serve more than 2 billion predictions per day using this library. So the takeaway for you, try to define a appropriate level of abstraction for your applications and libraries. And once you nail that, hopefully you are in a typed language, use types to express it. Try to automate as much as you can, and don't make mistakes. And this can help you to decrease your model runtime from months to hours. So one announcement I would like to make, if you guys want to join and gals want to join our pilot program, go follow this link. We actually fully open OP to a pilot access, and then we would just need your GitHub handle. And you might start using it, even today. No problems there. What else? For further exploration, there are talks from my colleagues, so go check it out. At Scale Conference by Shuba and Leah McGuire. Thank you.